Okay, in this podcast we're going to talk about how to calculate pH, pOH, and concentration. Hopefully at this point you've watched the podcast from Khan Academy on pH and pOH as an introduction, and you have a clear understanding of logs. Okay, so let's go ahead and get started. Alright, so one of the things we learned about in the Khan Academy podcast is that the equilibrium expression for the autoionization of water, where water breaks into either we can write it as H3O plus or H plus, is that the equilibrium expression is products, concentration of the products over the concentration of the reactants, right? But because this is liquid water, and liquids and solids, pure liquids and solids, are not included in the equilibrium expression. Therefore, the equilibrium expression is just the hydronium ion and the hydroxide ion. And we also learned that at 25 degrees C, the ion product constant for water is 1 times 10 to the minus 14. That's an important number that we need to know. It helps us solve a lot of things. Okay, so we want to calculate the H plus and OH plus in a neutral solution. So another way of writing what we just wrote is H2O, which is a liquid, becomes H plus and OH minus. And as we said, Kw is equal to the concentration of the H plus times the concentration of the OH minus. And because for every 1 molar of this, you get 1 molar of this and 1 molar of this, we could say that this value here, we can just square it. So the Kw is equal to the concentration of the H plus squared, and that's equal to 1 times 10 to the minus 14th. So if I take the square root, so the H plus concentration is going to be the square root of 1 times 10 to the minus 14. And if I plug that in, it's second square root 1 second EE negative 14. I get 1 times 10 to the minus 7. Molar. And so that's H plus OH. For every H plus I get, I also get an OH, so the concentration of that is going to be exactly the same. It should be 1.0 times 10, and this is 1.0, a little sloppy here, times 10 to the minus 7 molar. Okay. Okay, so we want to calculate the concentration of H plus for a solution in which hydroxide is 0.1 molar. Okay, so what we know is Kw equals H plus times the OH concentrations, right? And we know that Kw is 1 times 10, 1.0 times 10 to the minus 14th is equal to H plus concentration times OH concentration. So I know what this is, so I can solve for H plus. H plus concentration is going to be 1 times 10 to the minus 14 over the OH, which is given to me here, which is 0.010. So if I punch that in, I'm going to get 1 second EE minus 14 divided by 0.01. Oops, what did I do? 1 second EE negative 14 equals, divide that by 0.01, and what I get is 1 times 10 to the minus 12 molar, right? So that's A. For B, I'm going to use the same formula, right? This time I'm going to solve for OH, so it's going to be my KW over my OH concentration, and that's going to be 1.0 times 10 to the minus 14 over my OH, which is in this case is 1.8 times 10 to the minus 9. And if I divide those, I get 1 second EE negative 14 equals, divide by 1.8 second EE minus 9 equals, and I get 5.5 times, or 5.6 times 10 to the minus times 10 to the minus 6. I have two sig figs in both of these, so I want two sig figs in both my answers. This is 1.0 times 10 to the minus 12 and 5.6 times 10 to the minus 6. Okay. Alright, so pH is defined as the negative base 10 logarithm of the concentration of the hydronium ion. So what does that mean? Okay, so what it's really just saying is that pH is just another way of expressing concentration. So if I have, let's say, my acid concentration, or my H plus or hydronium is 0.01 molar, that would be 1 times 10 to the minus 1, 2 to the minus 2 molar. If it was 0.1 molar, it's going to be 1 times 10 to the minus 1 molar. Let's say it's 1 molar, it's going to be 1 times 10 to the 0. Right? It's just different ways of writing, scientific notation or not. If it's 10 molar, it's going to be 1 times 10 to the 1 molar, right? These are also molars. Let's just do one more. If I said it was 100 molar, then what I'm saying is 1 times 10 to the 2 molar, right? This number and this number are the same thing. So what we're saying is the pH in these cases is going to be simply the negative of the exponent. So in this case, it's going to be pH will be 2. In this case, the pH is going to be 1. In this case, the pH is 0, 1, and let me see. Let's do the log of 100. Let's do the negative log of 100. This would be negative 2, and this is negative 1. Okay? So it's just the negative of the exponent. That's all it is. It's just another way of expressing exponents. Okay. So we know this already. We know that in pure water, Kw, the equilibrium constant for water, is acid times the hydroxide concentration, and that is 1 times 10 to the minus 14th. And we know in pure water, both the hydronium ion and the hydroxide ion concentration are 1 times 10 to the minus 7th. So in pure water, the pH in pure water is going to be the negative of the log of 1 times 10 to the minus 7th, or 7.00. Now, one thing about pHs is sig figs are done a little bit oddly. We've got 2 sig figs here, so we want 2 sig figs in our pH, but we only count those digits after the decimal place. So this would be considered 2 sig figs. Okay. So we know that an acid has a hydronium ion concentration higher than that of pure water, so its pH is going to be less than 7. Okay, and a base has a lower hydronium ion than pure water. It's going to have a pH that's greater than 7. Okay. Alright, so we want to calculate the values for each of the 2 solutions described in exercise 16.5, and I wrote them here. For A, we said the hydrogen ion concentration is 1.0 times 10 to the minus 12. And if we take the negative of the log of this, we get just 12, right? And we could punch it into our calculator to show that we get the same thing. If I take the negative of the log of 1 second EE negative 12, I get, I don't have my negative there. Let me see if I just go up and add it. It's easier for me to just redo it. Alright, so if I take the negative, okay, if I take the negative of the log of 1 second EE negative 12, I get 12. Okay, here I can't do that with this because this is not a 1.0. If it were 1.0 times 10 to the minus 6, my pH would be 6. Now my pH should be close to 6, right, because that's what my exponent is here, but it won't be exact because of the 5.6. So for this one I need my calculator, so I'm going to take the negative of the log of 5.6 second EE negative 6, and I get 5.25 or 5.25 and 2 sig figs, so I need 2 sig figs. Remember, just after the decimal place are my sig figs, 2 sig figs. So it's close to 6. Okay, should be less than 6 because this is higher than 1. Alright, a sample of freshly pressed apple juice has a pH of 3.76, and we want to calculate the H plus. Okay, so what we said was pH is the negative of the log of the H plus, which means we said if I have a base 10, this is what I have. 10 to the minus 3.76, that's what the pH is, right? So I can plug that into my calculator. The 10 to the x is right here under the log. So I do second log of negative 3.76, and I get 1.7. I got 2 sig figs here, right, just after the decimal place, times 10 to the minus 4 molar. Alright. Alright, so here's a pH scale, and remember the most acidic, you have values that are 0 to 14, and in fact this is really designed a scale for weak acids and bases. You actually, if you have something, let's say that's 6 molar, it's going to be lower than 0. Okay, this only takes us to something that's about 1 molar, right? Okay, so we have a lot of stuff you can recognize from your home: lemon juice, cola, gastric juice, all acidic, right? And on the basic side, you have things like bleach and caustic soda. Okay, so the higher the number, the higher the pH, the more basic. The lower, the more acidic. Okay. Okay, so other P scales, pH, and the P in pH tells us we want to take the negative of the log of that number. Okay. So when we see the P in front of something else, the P of the negative P kW is the negative of the log of the kW, or the pKW. Okay, it's just the negative of the log of the kW, which would be the negative of the log of 1 times 10 to the minus 14, or 14. Okay, so because we know that the hydronium ion times a hydroxide has a kW of 1 times 10 to the minus 14th, we know that the negative of the log of the hydrogen ion plus the negative of the log of the hydroxide is going to give us a negative of the log of the kW, or 14. And because of that, we know that pH plus pOH is always equal to pKW, which we just calculated, which is going to be 14. And by knowing this, if I can use that, if I know, let's say, pH, I can figure out pOH. So if I know that the pH of something is 1.3, then my pOH is going to be 14 minus my pH, or 14 minus 1.3, which is going to give us 12.7. Okay? So lots of different ways to measure pH. We can use litmus paper. We have just plain old red and blue. An acid turns red. Okay, so blue paper turns red if it's acid, and the opposite, red paper turns blue if it's basic. We also have indicator paper that is range, that will turn different colors depending on what its pH is. We can use an indicator, and the indicator changes color whether it's in based on the pH range that it's in. We can also use equipment, in particular a pH meter or a pH probe. We have these pH probes that we use with the vernier and the Logger Pro that we can use to actually measure voltage. Okay, so strong acids, you got to memorize them. Got to memorize them. So it's HCl, HBr, and HI. So all the halogens, but not HF. HF is actually such a strong bond. Here, as you know, there's hydrogen bonds, so there's great resistance to pulling this H and F apart. It's actually a dangerous acid, but not considered a strong acid. Definition of strong acid means that they completely ionize. So if I put HCl in water, all of it comes apart, and I end up with H plus and Cl minus. There'll be no HCl as a molecule left. Okay, so the others you're going to know are nitric acid, sulfuric acid, chloric acid, and perchloric acid. And the strongest of all of these are perchloric acid. The more oxygens, the stronger. So these are by definition strong electrolytes because they break up into ions. And if they exist as ions, they're going to be strong electrolytes. Okay? So if I have a monoprotic strong acid, the hydronium ion concentration equals the concentration of the acid. So if I have a 1.2 molar HNO3, I also have a 1.2 molar H3O plus concentration, or we'd say a 1.2 molar H plus. Okay? It's because it breaks apart completely, right? For every one of these that I put in water, I get one of these or one of these. Alright, so let's find the pH of a 0.04 molar solution. So pH is equal to the negative of the log of the H plus concentration, and because this breaks apart into H plus ClO4 minus. It's also equal to the concentration of the acid, so it's the negative of the log of 0.040, 2 sig figs. So I want 2 sig figs in my pH, so I'm going to take my negative log of 0.04, and that will give me 1.397. So 3979. So if I want 2 sig figs, I got to round it to 2, and remember it's just after the decimal place, so I want 2 places, so it's going to round to 1.40 pH. Okay. And you should always check to make sure your pH is reasonable. If you put it in scientific notation, 4.0 times 10 to the minus 12, it should be within 1 unit of the exponent in this. Okay, you also need to know what the strong bases are. So strong bases are most of the soluble hydroxides. So it's all group 1, right? All group 1. So it's lithium, sodium, potassium, and on. And the group 2 hydroxides that are soluble. Okay, so if you remember, hydroxides are not soluble unless they are calcium, strontium, or barium. Okay, so other hydroxides are not soluble, but calcium, strontium, and barium are. So it's everything in group 1, the calcium, strontium, and barium hydroxides. Okay, and again, they completely dissociate in water. So if I have this, it's going to come apart completely as Ca plus 2 hydroxides. Come apart completely. It is not a two-headed arrow. Okay, for generalized acid dissociation, the equilibrium expression the equation can always be written generically as this. The acid, this is H plus some anion, plus water, gives me the anion and the hydronium ion, which I can also write as H plus, right? So the equilibrium expression is always the same. It's hydronium ion times the anion over the acid. And we call this, because it's special, we call it the Ka, or the Kc, but the Ka is specifically the acid dissociation constant. And the stronger the acid, the higher the Ka. And these are all, in fact, on this table here, these are all weak acids, right? Because if it's a strong acid, they completely dissociate, and it's 1 times 10 to the minus 7. Okay, so these are weak acids. All right, so I can calculate Ka from the pH. So if I have a pH of 0.1, of formic acid, and it's 25. Now the 25 is necessary when we're talking about using Kw of 1 times 10 to the minus 14th, because that assumes that it's going to be that constant only works at that temperature. Okay, so here we have HA. Let me actually make this a little bit, give me more room to write. Okay. Okay. So in order to solve this, we're going to, this is not a strong acid, right? This is, let me just get my ink tools back. What we're going to use to solve this is our Rice table. We know that K, we want to solve for what a Ka is, the acid dissociation constant, and we are going to use this equation, which we just talked about. So what we're going to do to figure this out is use a Rice table. So HA, and generically we can always use the same one, plus water, which we're not going to include in the calculation because it's a liquid, right? It's not included in the equilibrium. Always gives me some anion plus an H plus, right? Okay. So I'm given that I start with 0.1. So this is R. If I use a Rice table, this is what I'm going to have. I is my initial concentrations. I have a 0.10 molar of this. Initially I have none of this and none of this. Okay? And if I change, I'm going to lose some amount here. I'll just call that X. I'm going to gain the same amount here and here, right? Now I can actually calculate what the hydrogen or hydronium concentration is because I have a pH, okay? And I know that pH is the negative of the log of the concentration, right? So it's the negative, it's the 10 to the negative 2.38, right? So I can do second 10 to the x minus 2.38, and I get that the ion concentration, the hydrogen ion concentration is 0.00417, and I'm going to put that whole thing in there, and then fix my sig figs later. So let me change this to minus 0.00417. I'm going to do plus 0.00417 and plus 0.00417. Okay. So at equilibrium, I'm going to have 0.10 molar minus 0.00417, and here I'm going to have 0.00417 and 0.00417. So I can use this equation now. I know that Ka is hydronium times the anion over HC, the original acid. So Ka is going to be my H3O plus, which is right here, 0.00417. My anion is the same, so I can just square that, right? Over 0.1 minus 0.00417. And if I take that, I'm going to end up with, let me see, 0.00417 x squared is my numerator. I'm going to divide that by, in parentheses, 0.1 minus 0.00417, close my parentheses, and I get 1.8 times 10 to the minus 4th. Now let me just see sig figs. I got 2 sig figs here, so I want 2 sig figs here. This is also 2 sig figs. Okay, so that's going to be my answer. 1.8 times 10 to the minus 4. Okay. All right. We can also look at calculating percent ionization. That's a question that might come up in the AP exam. And we want to know what's the percent ionization of the previous example. So if we go back to that example, what we had was the acid concentration was 0.00417. That's how much acid we got, or H plus we got, versus what we started with the whole acid is 0.1. So let's go in and plug those in. So the H plus was 0.00417. My initial concentration was 0.10. And if I want it as a percent, I got to multiply it times 100. And I do that, and I'm going to get 4.17% ionized, which is pretty typical for a weak acid, right? If it was a strong acid, it would be 100% ionized. but this is much less than 100% ionized. Okay, so now I want to calculate the pH of a 0.3 molar solution of acetic acid. This is a weak acid, and I know it's Ka. Okay, so I have 0.3 molar. Okay, so let's set up a rice table. So I have RICE. I start off with 0.3 molar here of acetic acid. I start off with no acid, no anion. I'm going to lose some amount of acid and gain the same amount, so minus X on the left and plus X for each of these. So my equilibrium amount is 0.3 minus X, and here it's going to be X, and here it's going to be X. Okay, so I can say that my Ka, which I know, which is 1.8 times 10 to the minus 5, is equal to my hydrogen ion, or hydronium, times my acetate, over my, I'll just say my acid. Alright, so my H3O and my anion are both X, so this is going to be X squared, and this is going to be 0.3 O minus X. Okay, so let's just write what we have here so far. So 1.8 times 10 to the minus 5 equals X squared over 0.3 minus X. Now this can get real messy real fast. It's going to be a quadratic equation, because I'm going to end up with, if I distributed this, I'm going to end up with this times 0.3 minus this times X equals X squared. And one of the things we can do is simplify this. This Ka is tiny, -5, whereas this value here is 0.3. And what will happen is, if I multiply this X times 1.8 times 10 to the minus 5, I'm going to end up with a tiny number contributed by this X that will round to the same value it would be if I didn't use it. So if I get rid of the X, if I neglect it, and I should say that I'm going to neglect it if I neglect it, and I can only do that if this is tiny. Now this Ka is really tiny, so I can do that. So I'm going to end up with 1.8 times 10 to the minus 5 times 0.3, and if I do that, I'm going to get, let me see, 5. Let's just do that. 0.3 times 1.8 second EE -5. 5.4 times 10 to the minus 6. So I get 5.4 times 10 to the minus 6 is equal to X squared. So X is equal to the square root of this, and that will be, I'm just going to take find the square root function, square root, go up and pick this up, whoops, say enter again, and I get 0.0023 is my concentration, right? It's molar. So my pH is the negative of the log of that concentration, 0.0023. And if I punch that, I'm going to get, so I want the negative of the log of this, which I'm just going to go pick up. And when I do that, I get 2.63. Now I have 2 sig figs, so I want 2 sig figs. So that answer will be 2.63, because only after the decimal counts in terms of sig figs. Alright, so I want to calculate the percentage of HF ionized in 0.1 molar HF and in 0.010 molar HF. Okay, and I know Ka for, I can look it up in a table. Ka for HF is going to be, let me see if I can find it real quick, 6.8 times 10 to the minus 4. Okay, so this is a weak acid, right? So it's not all going to come apart. I know that Ka is going to be this, which is equal to my H. Let's just say we have HF becomes H plus F minus, right? And I know that the concentration of this times this over this is equal to my Ka. So let's figure out what the concentrations are going to be. Okay? So if I have 0.1 molar of HF, initial concentration here is 0. This is RICE. I'm going to lose some HF, gain the same amount of H plus and the same amount of F minus. So my concentration here is going to be 0.10 minus X. Here it's going to be X and X. So my Ka is 6.8 times 10 to the minus 4 is equal to my H plus concentration over my F minus concentration over my HF concentration. And that will be equal to X times X, which is X squared, over 0.1 minus X. So again, we could end up with this nasty quadratic equation. But I have a pretty small Ka, so I can actually ignore this. And if I do that, I end up with 6.8. Let's just write it out. 6.8 times 10 to the minus 4th equals X squared. I'm going to ignore the over 0.1 because I'm going to ignore the minus X, right? So X squared is equal to 0.68 times 10 to the minus 4, right? Distributing this times this. So X is equal to the square root of this, which is equal, let me see, so second square root of 0.68 second EE negative 4 gives me 0.00824. Okay, now we want to know the percent ionized. So this is what's the hydrogen ion concentration, and I'm going to put it over what the starting acid concentration is, which is 0.10. And I should write out what I'm doing. This is the H plus over the original HF, and if I multiply this times 100, I'm going to get this as a percent. So if I take 0.00824 divide by 0.1 and multiply times 100, I get 8.24%. Okay, so some acids are polyprotic, right? So HCl is a monoprotic. Each one produces one H plus. But I also have H2SO4. That'd be a diprotic, right? It's going to produce two hydrogens. And I could have phosphoric, which is H3PO4. That'd be triprotic, okay? So the difference between the Ka for the first dissociation and subsequent dissociations, let's see what they're talking about. So if I have H3PO4, the first thing that's going to happen is I'm going to end up with H plus. It happens stepwise, H2PO4, right? And if I then take that, I'm going to end with HPO4 minus 2 plus H plus, right? And then that can still lose one more, and a PO4 minus 3. And it's going to with plus 3 H pluses, right? So when it says the first association, that means losing the first hydrogen. Second association is when it loses the second hydrogen, and third is when it loses the third. So what it's saying is that the difference between the Ka for the first hydrogen and subsequent Ka values is 10 to the third or more. The pH generally depends only on the first dissociation. So most of the dissociation will occur here. Very little of it comes off on the second or the third. Okay? And here's the comparisons that we look at. This is the first, and this is the second. In the case where we have 3, we have 3. So let's take a look at how we'd use this. Alright, so the solubility of pure water is 25 degrees C. At 25 degrees C is 0.0037 molar. The common practice is to assume that all the dissolved carbon dioxide is in the form of carbonic acid, which is produced by the reaction between CO2. So the question is, what is the pH of 0.0037 molar H2CO3? So we need to find out what the hydrogen ion concentration is going to be. Now if we go back and take a look at this table, for carbonic acid, the first H plus that comes off is 4.3 times 10 to the minus 7. And the second is 5.6 times 10 to the minus 11. It's more than the difference of 10 to the third. So it looks like we can just look at the dissociation of the first hydrogen. And that compared to that, the second hydrogen is going to be insignificant. Okay? So we're going to use that K sub A is equal to 4.3 times 10 to the minus 7. Okay. So we have, we're going to have CO2 becomes H plus HCO3, right? Okay, so this is our, let's use a rice table. I start off with 0.0037 molar of this. I have none of this. I lose some amount of this, which is the same as what I gain here. My equilibrium is 0.0037 minus x. This is x, this is x. So my K sub A, which is equal to 4.3 times 10 to the minus 7, is equal to my H plus. I'm just going to say my H plus times my anion concentration over the acid concentration. In this case, that's going to be x squared over 0.0037 minus x. Okay? So if I look at this, let me just say that's equal to 4.3 times 10 to the minus 7. So if I distribute this and I multiply this value times x, this number is tiny, 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 so I can neglect this. And if I do that, I get x squared is equal to this times this. So let's put that result down there. X squared is equal to, let's see, 4.3 second EE negative 7 times 0.0037 equals is 1.591 times 10 to the minus 9th molar. Okay. me see, did I do that right? Alright, so x is going to be the square root of that, square root of this, which is equal to, so I want to take the second square root, I'll go up and pick it up, of that, and I get 4 times 10 to the minus 5. Is my concentration, and if I want to know my pH is going to be the negative of the log of this, so it's going to be negative log, let's just write it out also, negative log of 4 times 10 to the minus 5, negative log of 4 second EE negative 5 is equal to 4.4. Let me see. I have 2 sig figs. Where's my pen? 2 sig figs here. So it should be 4.40. Alright. Alright. Weak bases react to produce, bases in general react to produce hydroxide ions. So even if I start something that is not a hydroxide with a base, you know, obviously if I have NaOH, it's going to break apart to Na plus and OH minus, right? But I can even have a base like ammonia that doesn't have an OH in the formula, but when it reacts with water, the H plus comes over here and you're left with the OH, right? And that's where you end up with. Alright, so there's 2 general types of weak bases. One is, it contains a nitrogen and it's got the lone pair of electrons that accepts a proton, or it can be an anion of a weak acid. Okay, so if I have HC2H3O2, it could be the C2H3O2 minus, right? Alright. So if I have, let's say I have a base, it's going to, when it goes in water, it's going to end up giving me a base. Oops. If I start off with a base, it's going to give me a base plus hydroxide. Boy, I made a mess of that, didn't I? A base is going to end up, and this is not all that intuitive that it's written quite this way, right? But if I remember, I have NH3 and it becomes NH4 plus, right? That's the H base plus the OH minus that's left. So that's the general form you want to use. And Kb is the base dissociation constant. Here's the Kb's for a whole bunch of bases. These are all weak bases. Okay. We can use the Kb to find hydroxide concentration and pH. Alright, so we want to find the pH of a 0.15 molar solution of ammonia. And it gives us the Kb. But be careful with this because it asks for pH, which is the H log of the H plus concentration. So we need to first find pOH from the information and then use pOH plus pH is equal to 14 to find the pH. Okay. So here I have, let's use this as our rice. So I have, I'm starting with 0.15 molar of this. This does not come into the, so if I remember, if I go back to this equation, I want to start off with B minus. Okay, so the base is equal to H base plus the OH minus, right? Alright, so the Kb is going to be Hb times OH minus concentrations over the base, right? Concentrations. and because water is a liquid, it's not included. Alright, so I start off with 0 of this. Alright, I end up with, that's my initial. My change is I lose some x of that, gain the same x of these. So my equilibrium is 0.15 minus x. Here it's plus x, and here it's x. So my KB, which is 1.8 times 10 to the minus 5, is going to use this formula, which is going to be x squared over 0.15 minus x. And again, we'll end up with a quadratic equation, but we can look at this KB, and the value is tiny, it will be insignificant compared to this, so we are going to neglect. So I'm going to get x squared is equal to this times this, cross multiplying, so I have 1.8 second EE negative 5 times 0.15 equals 2.7 times 10 to the minus 6. So x is equal to the square root of that, which is, let me see, second square root. I go up and pick that up, and I get 0.0016. Okay, so that's my OH concentration. And if I want my pOH, it's going to be the negative of the log of this. So that'd be the negative of the log of that. And that will be 2.78. Now 2.78, I want 2 sig figs, right? Alright, so that's 2 sig figs. So that's my pOH. So because pH plus pOH is equal 14, 14 minus my pOH, which is 2.78, is going to give me my pH. So that is going to be, let me see, 14 minus that number is equal to 11.2. Let me see, 2 sig figs, so I want to have 2 places after the decimal, 11.22. Just make sure I did that one right. Yep. Alright, a solution can be made by adding solid sodium hypochlorite to enough water to make 2 liters of solution that has a pH of 10.5. Calculate the number of moles of sodium hypochlorite that were added to the water. So let's think about this. So sodium hypochlorite is going to be acting as a base, and I need to find the KB of it, and I looked that up on a table in the book, or it'll be given to me on the exam, and it's going to be 3.3 times 10 to the minus 7. Alright. Alright, so the pH is 10.5. pOH will be 14 minus 10.5, which will be 3.5. So my OH concentration is going to be 10 to the minus 3.5. So that's going to be, let me see, second EE negative 3.5. And that will be 3.16 times 10 to the minus 4. Alright, so let's set up a rice table. I have my ClO minus becomes HClO plus OH minus. And here I am starting with some unknown concentration. What I know is I end up with I start with 0 of this, but I end up with 3.2 times 10 to the minus 4th molar of this, right? It told me that right here. And because I have one of these for one of these, I'm also going to have that much of this. Okay, so if I'm gaining that much of this, I must be losing that much here. So my KB is going to be my HClO concentration times my OH concentration, oops, over my ClO concentration, and that will be 3.2 times 10 to the minus 4 squared, right? This and this, and this will be x minus 3.2 times 10 to the minus 4. Okay, and we know that that KB is equal to 3.3 times 10 to the minus 7. Alright, so again we could end up with a quadratic, or not. I'm going to go ahead and include it. Alright, so I end up with 3.2 times 10 to the 4th. Let's figure out what that is squared. Actually, I can just pick it up. X squared and that gives me that's going to be equals 10 times 10 to the minus 8th over 3.3 times 10 to the minus 7x minus this times this, which is 3.2 second EE negative 4 times 3.3 second EE negative 7. Oops. What am I doing? Let me clear that all. Alright. 3.2 second EE negative 4 times 3.3 second EE negative 7 equals 1.06 times 10 to the minus 10. See why it's sometimes eliminated? It's just such a tiny number, it's going to be insignificant. Okay. Okay, so what I should have written here was this, which was 10 times 10 to the minus 8 is equal to 3.3 times 10 to the minus 7x minus 1.06 times 10 to the minus 10. Okay? And if I do that, I can add 1.06 times 10 to the 10th here. So I have 10 second EE minus 8 plus this number here equals, I end up with 1.00 times 10 to the minus 7th, which is essentially what I had here, equals 3.3 times 10 to the minus 7x. So x becomes this divided by this. So I'm going to take this number and divide it by 3.3 second EE negative 7. And whoops, didn't like that. I'm going to take 1 second EE negative 7 divide by 1 second EE negative, I'm messing up my EE's, 1 second, alright, second EE 1 second EE negative 7 divide by 3 oh man, I think I'm getting too tired. 1 second EE negative 7. Alright, divide by 3.3 second EE negative 7 equals 0.3, it's 30. Okay, so that's the concentration of my sodium chloride I started with, right? But if I want to make that concentration, and I have 2 liters of it, molarity equals moles over liters, right? And we want to know the number of moles. So my molarity times moles is molarity times liters, and I have molarity of 0.3. My liters is 2, so I need to double that, and I end up with 0.6 liters, or 0.6 moles. Ooh, that was tough. Okay, so we know Ka and Kb, the product of those two gives us Kw. So if we know one of them, we can calculate the other. These are pretty easy. So we want to calculate the base dissociation constant, which means Kb, of the fluoride ion. Alright, so in order to do that, I need to look up the Ka of HF. And if I look that up, and this again will be given to you, but the Ka of HF is 6.8 times 10 to the minus 4. Okay? So Kw equals Ka times Kb, and I'm trying to find Kb, so Kb is equal to Kw over Ka. So Kw is 1.0 times 10 to the minus 14. My Kb, my Ka is, I looked it up, is 6.8 times 10 to the minus 4. I divide those two, I get, let's see if I can punch this better this time, 1 second EE minus 14 divide by 6.8 second EE minus 4 gives me a KB. I want 2 sig figs because that's what I have in both my KA and my KW. So it's 1.5 times 10 to the minus 11. Okay, I'm going to do the same thing for the ammonium ion. Okay, so the KB for ammonium is the Ka. This is a base, so I'm going to look up the Kb. I'm trying to find the Ka. So the Kb is 1.8 times 10 to the minus 5. I don't know why I'm buzzing all of a sudden, but alright, so my Ka is equal to my Kw over my Kb, which is 1.0 times 10 to the minus 14 over 1.8 times 10 to the minus 5. And if I plug and chug, I'm going to get 5.6 times 10 to the minus 10. And we're going to stop there.